Welcome to this explainer. Today, we're diving into the massive yet totally hidden world of micro and nanofabrication. We'll be unpacking some incredible research by Shubhdeep Bhattacharjee from IIT Hyderabad. Think about it. If you're watching this on a smartphone, working on a computer, or even just driving a modern car, your everyday life literally depends on the technology we're about to explore. Now, to really grasp why this matters right out of the gate, take a look at this number, $750 billion. That's the size of the global semiconductor market right now. To put that into perspective, this single industry is rivaling the entire gross domestic product of Switzerland. Yeah, a country that sits at number 20 on the global GDP list. It's just a colossal economic engine. So here's our roadmap for today. First, we'll look at the trillion-dollar chip economy. Then we'll track the shifting eras of technology. And finally, we'll get into the actual science of sculpting at the nanoscale. All right, let's jump straight into part one, the trillion-dollar chip economy, the macro perspective. You see, global semiconductor demand isn't just growing, it is accelerating. We're looking at a massive compound annual growth rate of 8.8%. By 2032, this market is forecasted to smash right through the ceiling and exceed $1.3 trillion. This wild growth really just represents the complete digitization of our world. I mean, from memory devices to logic components, there's just this insatiable global appetite. Now, if we look at the overall global market for semiconductor manufacturing, it kind of looks like a relatively well-distributed pie. South Korea has the leading edge at 25%, followed really closely by Taiwan and China at 22%, then Japan at 13%, and the Americas at 8%. So at first glance, you might think, okay, this is a pretty balanced global effort. But, well, the reality of high-end technology is a little more nuanced than that. The really crucial point pops out when we isolate just the advanced foundry capacity. We're talking about the bleeding edge stuff here, those next-generation 3D transistor architectures that power the most advanced AI, the newest smartphones, and supercomputers. When we look there, Taiwan completely dominates with a massive 68% hold on the global supply. South Korea and the US are sitting at just 12% each, and China at 8%. So suddenly, when it comes to peak innovation, that pie isn't looking so evenly distributed anymore, is it? So what does that kind of dominance actually mean for a nation? Well, for Taiwan, which is a region with a population of 2.4 crore, so about 24 million people, this single industry generates $150 billion. That is an absolutely astonishing 20% of their entire GDP. It really proves this vital modern equation, right? Cutting-edge technology innovation plus massive economic incentive equals supreme national importance. Semiconductors aren't just computer parts. They are literally the geopolitical bedrock of the 21st century. Which brings us to part two, shifting eras of technology and the historical context behind all this. If you look back, you can track the defining technological pursuits of modern history in these really distinct phases. Between 1920 and 1940, the world's brightest minds and biggest budgets were all poured into defense technology. Fast forward to the 60s through the 80s, and our eyes turned to the stars. Space was the ultimate frontier. But then, from the 1980s all the way to today, our frontier completely shifted. We went from the vastness of space to the microscopic. Semiconductor technology became the defining pursuit of our era. But how do we actually progress in this current microscopic era? It usually starts with pure concept and incubation happening in academia. Think about the complex 3D transistor designs like FinFET that originated over at UC Berkeley, or the groundbreaking extreme ultraviolet light patterning, commonly known as EUV, which was born at MIT. Those foundational concepts are then handed off to industry for integration in mass manufacturing. It's this absolutely vital pipeline between university labs dreaming up the impossible and then the industry figuring out how to print it, a trillion times over. All right, let's move into part three, sculpting at the nanoscale, where we actually step inside the clean room. A really helpful way to wrap your head around nanofabrication is to think of it as the art and science of 3D printing plus sculpting structures at the nanoscale. I want you to just think about that for a second. We aren't just snapping pre-made parts together here. Engineers are literally molding and shaping materials at dimensions completely invisible to the human eye. It basically comes down to two core processes. First, you have additive manufacturing, which acts a lot like a standard 3D printer, laying down exact layers of material only where we want it. Then, conversely, you have subtractive manufacturing. That's kind of like carving Michelangelo's David. You're removing the excess block of material to reveal the intricate structure hiding underneath.
Believe it or not, nanofabrication uses these exact identical principles. We are adding thin films and then delicately etching away what we don't need, just on an atomic scale.
Now, because these dimensions are unimaginably small, we're talking sometimes just a few atoms wide, this nanosculpting obviously can't happen in your average factory. It has to happen inside heavily regulated clean rooms. The workers there have to wear these specialized suits, operating in environments often bathed in yellow light, just to prevent any unwanted chemical reactions on the silicon wafers. In this space, even a microscopic speck of dust acts like a massive boulder crashing down, completely capable of destroying a microchip. It is an environment of absolute, unforgiving precision. So we've seen how trillions of dollars, intense global power dynamics, and really our entire defining technological era all rely on humans in specialized suits, meticulously adding and carving away atoms in these pristine clean rooms. But as we know, technology never stops. As we rapidly hit the absolute physical limits of how small we can possibly sculpt silicon at the nanoscale, we're left with one really critical question. What technological era comes next?